We now want to move into the far more chemically sounding idea of enthalpy. So enthalpy has the symbol of capital H. This is why heat doesn't get it, why heat gets Q, because enthalpy is a capital H. And this corresponds to something akin to the total heat content of a system. So what that means, remember heat, it has to do with this thermal energy. So enthalpy is looking at quantifying the thermal energy within a system. Temperature is the average thermal energy of those molecules, how much they're moving. But when we're looking at enthalpy, now this is an extensive property, so more water has more enthalpy. But we're also looking at, kind of how much they're moving and how many we have. And so it's kind of a way to quantify that. We generally don't care too much about actual enthalpy, like, the enthalpy of the system is 100 joules or something like that. Instead, we more look at changes in enthalpy. And the reason for that is that at constant pressure, delta H, so the change in enthalpy of a system, is equal to the heat associated with that same change from the perspective of the system. This is very useful in a chemical context because all chemistry occurring under the atmosphere happens at a constant pressure. So every reaction that we do in the lab, every reaction that's happening inside your body, inside your car, inside all of the kind of normal existence is all happening at a constant pressure. And so what that means is if we're measuring the heat associated with a reaction, or we're interested in knowing the heat associated with a reaction, either because we want to use it to heat things up or we want to make sure we have enough heat to make it happen, we can characterize the heat associated with chemical reactions by quantifying the delta H of that chemical process. So as we move forward talking about the heat of chemical reactions, we're going to use the delta H to talk about those. And so when we talk about delta H, we're going to use the same sign convention that we had for heat. Delta H greater than 0 means energy goes into the system. The enthalpy increases of the system, so that means energy has gone in, there's heat that has gone in. Delta H less than 0 means the heat has left. So this exothermic is again the idea of releasing heat. So specific reactions can be classified as being either exothermic, where the heat leaves the system, that would be a negative delta H, or endothermic, where the heat goes into the system. That would be a chemical reaction where delta H is greater than 0, where it's positive. In these cases, when we're talking about chemical reactions, they're always going to be the system that we talked about in the last set of videos, right? The idea that something that you're interested in, how does the heat change for that? Whereas the solvent and the air, what's around you, what's around that, that's the surrounding. So if you run a chemical reaction in water, the water is the surroundings, and the actual reaction itself that's dissolved, and those molecules that are dissolved in the water, those are the system. So the same characterizations of endothermic, exothermic reactions as we saw previously is still going to apply. When the heat is greater than 0 for the system, the delta H is greater than 0, that's endothermic, and the surroundings tend to get colder. So for then an exothermic reaction, the surroundings tend to get warmer. So when you burn wood, energy comes out of that. The surroundings get warmer. There was enthalpy content inside the wood that it has now decreased, and that energy has been released as heat to the surroundings. So the air around the fire, or your hands close to it, get warm. That energy was stored within the logs. Now it's been shared with the surroundings. When we talk about these delta H, it really is some sort of variable, right? Enthalpy is a variable of the system. And if the delta H is negative, that means you really have had a decrease. The reactants had a high amount of heat content, and the products have a lower heat content. So that enthalpy has gone down, and the energy has to go somewhere out into the surroundings. So conversely, for endothermic, the delta H has to go up, right? So our delta H has gone, or our H, sorry, has gone up. The delta H is positive, which means that the heat had to go into the system. So enthalpy is a characteristic of a chemical reaction. So it's going to be really common that when we write chemical equations that we explicitly feature the enthalpy change. We call that a thermochemical equation. So CH4 plus 2O2 gives me CO2 and H2O. And the delta H associated with that change is negative 890 kilojoules per mole. Okay, so we just write the delta H right next to it. The negative sign on delta H is indicating the fact that it's exothermic. So whenever we have a negative delta H, that's always exothermic. And then we see that per mole, it's kilojoules per mole. So each mole of reaction yields 890 kilojoules. So a mole of reaction would be one of those, and two of those gives me 890 kilojoules. And I know it's going to be released. We can also rewrite chemical equations where the heat is featured, as part of just the line, right? Plus the heat. In this case, the heat is featured as a product because it's an exothermic reaction, right? But you'll note we don't put a coefficient there. All the coefficients that are already there, the ones and the twos, we can just use those as we need to when we want to do stoichiometry with this heat value. For an endothermic reaction, we can see that our delta H is positive, right? We don't write the positive, but there's an implied that the delta H is positive there. So we know that means it's endothermic, and when we write that, we can see we want to include it in the equation, it becomes a reactant because the heat is going in, right? The heat goes in, you need 28 kilojoules per mole going into the reaction. We know that that heat has to come from the surroundings. So when you dissolve ammonium nitrate right here, NH4NO3, when it dissolves in water and becomes aqueous ions, we can see that that has heat go in. So it comes from the water. The water gets cold. This is actually how instant cold packs work. You just dissolve ammonium nitrate in water, and the water gets quite a bit colder. With endothermic reactions, we have a tendency to associate them with cold, which is right. Endothermic reactions cause the surroundings to cool down. But there's also other endothermic reactions that are a little more confusing, like boiling. Boiling water is endothermic, because really what endothermic means is that energy goes in as a reactant. It drives the process to happen. So when we boil water, the heat causes the reaction to occur. Obviously that boiling water is hot, but there's a lot of heat associated with it, but really technically you are making the surroundings colder. In this case, the surroundings is just fire. So the fire is getting colder because that heat is going into the water. So these endothermic reactions, in order to happen, heat has to go in. So photosynthesis, the process where plants turn sunlight into energy, namely sugar, that is because that energy is an endothermic. It's part of an input. You need to have that energy go in order to make the chemical reaction occur. In this case, as sunlight, but still it's that energy going in. Participation 616, question 4. Classify each of the following processes as exothermic or endothermic. A, the dissolution of NaOH in water causes the water to become warm. B, an instant ice pack is activated, it becomes cold to the touch. C, in the combustion of propane, a bright flame is produced. And D, 2H2 gas plus O2 gas yields 2H2O gas plus 43 kilojoules per mole. This is the fourth question on participation 616 due Tuesday, June 16th at 11:59 p.m. over on Blackboard. Link to the assignment is right below links to these videos. Classify each of the following processes as exothermic, endothermic. Again, we got A, dissolution of sodium hydroxide in water, causes water to become warm. B, when an instant ice pack is activated, it becomes cold to the touch. C, in the combustion of propane, a bright flame is produced. And D, hydrogen and oxygen react to make water in 483 kilojoules per mole. Okay, another participation question. How many? Yeah, we still got 2 videos left. Okay, so still a couple more videos left. Looking for more participation questions. See you in the next video.